for the kind introduction, and of course also a big thank you to the organizers for bringing together this kind of very different audience also. And I'm really happy to be allowed to speak here and tell, kind of also introduce and set the stage for antiferromagnets and altermagnets. And then later also talk a little bit about the work that I have been doing. So first of all, antiferromagnetic spintronics is a very vast field where many different developments have been occurring in the, I would say, last 10 to 15 years now. And there is, of course, the central thing is kind of the antiferromagnetic structure here, this typical collinear arrangement of having two sublattices, A and B, that are aligned in antiparallel fashion. And then you try to harvest the properties here, especially kind of you find fast dynamics in the terahertz regime that you can investigate due to the magnetic excitations that are inside the antiferromagnet. Then one of the important milestones was really showing that you can also electrically switch antiferromagnetic systems, so you can influence the order parameter in these systems. And now in this talk today, I will first introduce kind of work that has been done in the direction of, on the one hand side, non-collinear antiferromagnets, where you typically have a free sublattice structure or a more complex structure. And there are very intriguing effects like a tunneling magnetoresistance effect that has been now observed at room temperature. And then this field of altermagnetism I will introduce. I need to be honest, I have not done any experiments really in this direction, so I'm not the expert. But there are two fantastic speakers afterwards that will tell more about these effects. And later on, I want to talk about Magnon spin transport in these systems. Now, before delving deeper into non-collinear antiferromagnets and also altermagnets, I want to at least briefly mention one of the issues that you sometimes encounter when working with the antiferromagnets, and that is definitely the magnetic domain structure that you might encounter when you work with antiferromagnets. So there is a large, let's see if this now, okay. There's a large difference in different domain orientations, all of these that can form in an antiferromagnet. So per se, already this kind of two sublattice nature, what is sublattice A, what is sublattice B, this is kind of not directly set. There can be symmetry requirements and all of these things. And then you have defects and all of the additional problems if you make materials out of that, that will lead to domain formation. And you need to be aware of these domains that might influence your measurements. And there's Helen. She already, back in 2002, and I think 2001 was another publication, discussed mechanisms that also lead to the formation of domain structures. And one of the important things is also, if you think about structuring this thing, so this is kind of a nickel oxide platinum structure here, where strain effects is one of the important things that you need to think about. Magnetoelastic coupling in combination with the strain that you have here and stress release that you might form will then lead already to a domain formation in the system. And the nice thing is that this, interestingly, this strain and magnetoelastic coupling leads to some phenomenologically that remind you of a typical ferromagnetic structure where dipolar effects need to be encountered if you think about these boundaries here on the right-hand side that then lead to this domain closure formation that you see in the system. There's also some work now back on one of the working horses in antiferromagnetic metallic systems, CUMNAS, where now there has been done some work in transmission electron microscopy where they really try to see how sharp these domain walls can be. And in this work here, published in Science Advances, they looked into epitaxially grown thin film structures on a gallium phosphide substrate, and they saw some edge dislocations, as is shown here in this cartoonish picture here, where you have now a transition between two domains. And with the resolution that they achieved in their TEM studies, they could really show this is atomically sharp interfaces. So this domain wall is very thin, and you immediately transition over within just this one spin step here or even here without having any spins in between these two domain walls. So you will not really find any domain wall in the system, but there are just these two domains in the system atomically sharp defined in these structures. So that's also something one should consider. Now, why is there some movement in antiferromagnetism and what's going on there? So initially, spintronics dealt a lot with ferromagnetism, and this comes in the end from the fact, so you have already time reversal symmetry broken in the system via the magnetization, and in this way you get spin split bands for the electrons. So you can use them immediately to get a spin polarized current. This allows you to manipulate, in the end, also the magnetic order parameter via the spin polarized current, and you can work with that. So that is the workhorse. If you think about giant magnetoresistance effect, tunneling magnetoresistance effect, all comes back to this spin splitting that you have in the ferromagnetic systems. In the antiferromagnet, if you think about the collinear structure, and you think about now doing a time reversal symmetry operation, of course now these two spins here will change their orientation. But if you do a translational operation in addition, you will maintain, again, the same antiferromagnetic structure. So with this translation and time reversal symmetry operation, you get back to that, and due to that, you have Kramer's spin degeneracy again kicking in. And this means in the electronic structure, you will expect now to have degenerate electron bands in the structure. So there's no spin splitting per se. Of course, you can always go relativistic and use spin-orbit interaction that allows for spin splitting, but a question that arose in the last 10 years about is, are there other effects or more robust effects that we can use to introduce a spin splitting in this? And this will be, on the one hand side, it will show non-collinear structures where you can observe effects that point to the fact that you can get some spin-dependent effects. And finally, then, Altham magnets where you get a spin splitting due to a special symmetry that you need to obey in these structures. Now, in the non-collinear antiferromagnets, the business was kind of started by a theoretical work published in PRL in 2014, where they looked into these typical manganese-free iridium structure here on the left-hand side, that in this theory model, they put down on this Kagome-Lette structure and looked into these spin structures where you have these spins pointing either in, as it's shown in these structures here, and then thought about, is there something where we can work with and define a finite Berry curvature? So normally, if you think about this Berry curvature, you will figure out that the Berry curvature, due to the time reversal and inversion symmetry that the system has here, should be zero in these structures and should vanish. But what you can do is, there's two things you can play around. The first thing that they tried to do was really breaking a little bit time reversal symmetry by applying an additional magnetic field in this out-of-plane direction. You count the spins a little bit out of this plane, and with that time reversal symmetry breaking, you can introduce some finite Berry curvature in the system. In addition, you can also allow for a special spin-orbit coupling structure that is kind of depicted here with these arrows between the sites where the actual spins are, the localized spins are remaining in that structure. And with a certain symmetry, you will also get some finite Berry curvature in K-space as it's depicted over here in these calculations that they showed. From that, they calculated then one of the interesting properties that is a so-called the transversal conductance, so what kind of a Hall effect structure signature that you can get out of that. And they could even show that you get very large values if you account for spin-orbit coupling in these structures, and two different magnetic structures that are possible in the system will also give you opposite signs in these structures. And that then triggered experimental work to investigate these. This is now work on a single crystalline, published a year later in Nature, where they worked with manganese-free tin in this sample. So you have, again, this kind of structure here. If you project it down onto one plane, that reminds you of the work that's been shown there. Important is now you have these spins here pointing in a certain direction. That is kind of the easy direction here along this line here, for example. And now you can, due to an effect of slight magnetic anisotropy, you still have a net magnetic moment, so the spins cant a little bit away from this direction as indicated here. And you can measure magnetization as a function of the magnetic field. The magnetization that you get is rather tiny, so you see it's milli-mu Bohr per formula unit, so compared to a ferromagnet, completely small. But in certain, so it arises as long as you go below the Néel transition temperature of the sample, you see even a hysteresis for a field now applied in these special directions. And if you apply the field in this outer plane direction, you see not really any response, only this Cantian response of the structure. So the nice thing here from the experimental side is you have this hysteresis where you can selectively go from one certain configuration here. So for example, these spins here pointing up or these spins pointing down. And in this way, you can selectively go into two different magnetic configurations, and you would expect that this gives you an anomalous Hall signal. And indeed, this was the most important finding of this work. You can see now that there is a finite Hall signal that they observe in this structure, so driving current in one direction, measuring the voltage drop transversal to it. And it shows hysteresis similar in these field values that you have seen before from the magnetic measurements. So by selectively switching between these different magnetic configurations, they achieve the switching of this Hall voltage signal. And the values that they extract from this, if you compare that to typical ferromagnetic systems, it's already quite sizable, really large effects that you see here in this manganese-free tin structure. And this then also was followed up by Helena in her work, looking also into additional effects that you can use. So there you used now a charge current to look into an anomalous Hall voltage that you can generate. Here now you work with a temperature gradient to generate then the anomalous Nernst effect in these structures. And I think Helena will tell a bit more about this. No? Okay, then I can talk a little bit more about it. Great. So again, the important thing is kind of you can switch now, or you will have domains with a different magnetic configuration. And in the setup that has been used here, you scan now a small laser spot across your sample to image these magnetic domain structures. And using now the fact that kind of your anomalous Nernst voltage will change sign depending on what domain you will be in, you get also a spatially resolved image of this domain structure in the system. And you can also do magnetic field dependent measurements where you now sweep the magnetic field and kind of average out these voltage values that you get. And you see a nice hysteresis loop and a finite anomalous Nernst effect in these structures. So this is, I think, also a very important step to show, indeed, independently what drive you use, you will get anomalous Nernst or anomalous Hall effect in these systems. Another step that is important for us in spintronics is also looking into charge to spin current conversion. So if I drive a charge current through the system, am I able to get to a spin current in a transversal geometry, so this classical spin Hall picture that allows you to transform currents. This has been then shown for this manganese-free tin structure, again in a Nature publication in 2019, where they looked into two different processes. On the one hand side, really the direct effect. So you have here this manganese-free tin single crystal where you drive a charge current through it. And the idea is now that at the top surface, you will get a spin accumulation that you want to probe. And for this, they attached a permalloy spin detector and a copper reference electrode to measure this voltage drop here on the top. And indeed, what they see in the experiment with that magnetic field sweep, you only switch this permalloy electrode, so this will switch your voltage sign that you will get out of these measurements, but the magnetic field is too small to influence this domain structure, but they prepared it beforehand by applying large enough magnetic fields, and you see this step-like behavior here. So there's indeed an effect that you see here in the structure due to the charge current leading to a transversal spin current in the system. They also did the opposite way around. So here you have charge current drive. Here now they switch to the spin pumping geometry where we already heard some comments about previously. So the permalloy here is driven by a microwave field, and now you measure the voltage or the rectified voltage in the end that you get out of the system. And also there they find a very peculiar symmetry in the system that is no longer following the typical spin-Hall geometry, but can be nicely explained by the spin structure that you have in the system, because here the magnetic fields are already sizable enough that you can selectively orient these spins also in the system. Last but not least, this has been last year, and I think this was one of the most exciting results that I saw there, is you can take manganese-free platinum now in this system. So again, this non-collinear spin structure. And what they did is really forming a tunneling structure out of it. So you have a magnesium oxide barrier separating two manganese-free platinum layers in the system. And in addition, one of these manganese-free platinum layers is exchanged biased by an additional antiferromagnetic manganese platinum layer. And if you measure magnetization, again, I mean, the effects are tiny in regards to magnetization, but you can still resolve it. You see that you have now this shifted hysteresis loop for one of these manganese-free platinum layers. And this allows you to kind of achieve a magnetic configuration where this one will point in an opposite sense as this one here as a function of magnetic field. And if you now measure really the tunneling current across the structure here, as it's shown down here for the resistance area product, you see the resistance really changes by a factor of 2 here in this special device. And they were honest that they fabricated a lot of different devices, but still you see that you get at room temperature finite tunneling magnetoresistance values with these structures, and can now go also to think about some applications, because I mean the size is already quite large. Now questions would arise how you can switch that system faster to go for memory applications maybe in the future. And now I have the honor of talking about altamagnetism. As said, I'm not really the expert. The experts are these guys over there. They're so famous that they also earned from me some distinction that I gave them some alias names. So you can figure out why they are named this way. The altamagnetism, so we talked about already kind of this time inversion plus translation symmetry in a system that leads to this Kramer spin degeneracy in an antiferromagnetic structure if it's collinear. Now in this work that has been pioneered by Libor, Jairo, and Tomasz, they showed that in addition to just looking into this magnetic ion that you have in the structures, you should also think about the surrounding. So going back to the old days, you would say, okay, the crystal field is one of the important things that you need to think about in these structures. And here's one example. This is ruthenium dioxide, where if you look in this, just a plane cut of the structure, you have these 4 oxygen atoms that surround the ruthenium in the middle. And if you now look into these structures and you think about what would happen now if I do this time reversal plus translational motion to get back to the original state, the issue is that due to this coordination here that I have, that this short axis of this this route here is kind of a little bit shorter than this lengthy axis here, I'm not able to do this anymore. So I have a broken time plus translational symmetry in the system. And this immediately has an effect on the spin bands of the system. So what I see there, that kind of here in the center, that's the gamma point. And if I go away from that highly symmetric gamma point in certain crystallographic directions now in these structures, I will see that I get spin splitting in these bands. So here you see the red one should be, for example, spin up, blue one spin down. So they split, and at the edge of the Brillouin zone, they will merge again together. So, of course, this can have now different symmetries in the system. And this was then what coined the term altamagnetism. So here, again, the example for ruthenium dioxide, where you kind of see, depending on which directions in K-space you move, you will either have kind of, this is now a cut at fixed energy, you will have either spin up or spin down, and it alternates in a fashion. You already saw, and we'll talk about this in a moment, this is very similar to this more complex ordering phenomena in a superconductor when you think about a D-wave superconductor and all of this. So that also led to this classification scheme that we'll come to in a moment. And now here's also some structuring where you see that this spin splitting is not only happening for a specific band in the system, but it is also found in different electronic bands at higher energies. With this, you have you can think about the structure now in this ruthenium dioxide as these two shifted cones here, and now depending on the electric field and the orientation of the electric field that you apply, you can either generate a spin polarized current by going along one of these directions, but if you point the electric field along these nodal lines where the two spin bands are degenerate in this direction here, you still get a transverse spin current. So this gives you the opportunity to either think about, we're using that for magnetoresistance effects, so really working with an antiferromagnetic system and getting sizable magnetoresistance effect, or also thinking about spin transfer torque effects. So you can put another material next to it and then drive dynamics or also switching in these systems. And I was already referring to this kind of similarity that you will see there, that indeed, if you think about the structure that I've been showing to you, so this shifting or alternating orientation of these spin bands, you find node structures also where there's the degeneracy is still there, and then you find values where they have a spin splitting at the Fermi energy in the system. Similar if you think about a D-wave superconductor, where now the phase alternates in this. But if you would integrate over this whole area here, similar as over there, you will not get a finite spin splitting or finite phase here, so it averages out in the end. There has been lots of work, and this is not the most updated one, finding candidate materials. The interesting thing is that the symmetry argument you can apply to many, many different antiferromagnetic materials that have been already around. And Libor, Jairo, and Tomasz are also heavily putting forward new candidate materials. So this is now out of their physical review X that's already 2 years old, so there are much more that are now available. But you find here this ruthenium dioxide, which is characterized as this D-wave structure. You can also find other ones that give a more complex structure in a system where you have now more nodal lines in the system, which make, of course, the symmetries that you need to consider a little bit more complex. And there's it started with D-wave, G-wave, and I-wave. Nowadays, there's also proposals how you can work with this in a P-wave picture, where this most critical thing is that they now also think about non-collinear spin textures to achieve this effect in these structures. Now, of course, this is nice theoretical work, but you also need to really prove that this effect exists in these structures. And for this, one of the most intriguing results, I think, was now out in Nature this year, where they looked into angle-resolved photoelectron emission spectroscopy to really identify the spin splitting. So they worked with manganese telluride, which is this typical G-wave structure. So here's a depiction of these nodal planes. You have one in the middle here, and then you have these 3 additional ones that go into these K directions in the crystal structure. That's the hexagonal crystal symmetry that you have here. And now the expectation would be that here, if you take the electron band dispersion along these nodal lines here, this will give you no spin splitting, but as soon as you go to a different direction, here along this M direction, for example, or M dash direction here on the top, you will see a spin splitting that also will alternate if you go into the opposite direction in the system. And you have now here experimental structure here. One in the case, you see it down here, it says that it is in the K direction where you're looking at, and you see only a very vanishing small splitting in this, which also nicely agrees with the theory calculations that are depicted over here, that also take now into account spin orbit effects in these structures. In the other case, when you now look into a different crystallographic direction, what you see there is that there is at least some splitting here. It's, of course, difficult to resolve in this experimental technique, but this nicely also agrees with the theoretical calculations that they have here. So there's some indication here. Of course, the one thing that would be here still missing is really showing that this is also a different spin orientation. So this was not spin resolved, but this will be, I think, the next step in regards to the ARPIS data, that they will also try to spin resolve these experiments. The other thing, and I think this you will also not. Oh, gosh, I'm really bad at guessing. So there is, of course, also now, due to this effects of this spin split structure and the additional symmetry breaking, you will also expect that these systems show a anomalous Hall effect. So ALTHAMMER should be showing this behavior. And this is now an example from Helena's group, also showing that there is a Hall signal that you can get out of this ruthenium dioxide structure. You need to really apply large magnetic fields in the end to really go into a saturation, but this is now with in this nice publication here has been now shown that indeed you find some saturation. Again, you find only a very small magnetic moment, which is not kind of accounting for this large Hall signal that you get in these structures. And this can be one of the indications that there might be ALTHAMMER signatures in the system. Then there was also some work, so we talked already about charge to spin current conversion, and also this idea, if you apply the electric field along one of these nodal directions, you would expect to have a transverse spin current, and this has been shown in this Nature Electronics publication 2 years ago, that indeed in ruthenium dioxide, if you have a certain crystallographic orientation where you apply your electric current and a certain termination, this gives rise to very interesting spin transfer torque effect. So on top of this ruthenium dioxide, they placed again a permalloy structure to investigate either with second harmonic Hall or the FMR spin torque measurements, this spin torque effects. And what they saw is that, okay, this geometry here, this is a typical spin Hall effect that you also would get if you take a heavy metal with a large spin orbit coupling, where if you apply an electric field, you will get spins with this orientation here on the top and at the bottom of the structure. But in these ruthenium dioxide, you have also the possibility to get to spins that are oriented in this fashion, that they point out of this top plane, which you would not expect, and also a way to have these spins. This comes from the fact that now you can also control this orientation of your spin via the Néel ordering parameter. So taking different orientations will allow you to selectively get to this. And with this nice torque here, you could think about switching also perpendicular magnetic anisotropy structures with that system, and it's a very efficient one. Finally, in these systems that we talk about, there's not only the electronic bands that one can consider and look into the ALTHAMMER properties that come from this new symmetry that you need to consider, but also there is a contribution that you need to think about in magnons, should be also there if you think about phonons, in these ALTHAMMER, that you will find a characteristica that is normally not considered. So first, if you take a collinear antiferromagnet and you think about the magnonic structure, you will find that initially, disregarding any further contributions, you will have two magnon modes that are energetically degenerate, and they have opposite chirality in the system, but completely lying on top of each other through the whole Brillouin zone that you have. In an ALTHAMMER system, you will have now a structure that allows you to also observe some finite splitting if you go away from that gamma point. At the gamma point, again, due to the symmetry restrictions, you still have degenerate bands, but they should split up here. And this is now work from Libor back last year when I showed these structures that they calculated for ruthenium dioxide. And Helen, you will talk about more about these symmetries, so at least one guess was right, one can now look into these structures. One of the challenges, of course, if you want to resolve that in the experiment, well, you need to look first, of course, on this energy scale here. So we're talking about a couple of 10, 20, 40 millielectron volts, typically now in ruthenium dioxide. And you need to be able to kind of look into directions where you have finite K value, which is rather large in typical geometries and not close to this gamma point, which is the more easy way. But I think Helen will tell you more about this. Okay. With this, I'm kind of hopefully have set the stage for the next two speakers, as this is just the appetizer. But I want to share with you that this is one of the very intriguing things, I think, now for antiferromagnetism, that you find some very nice functionality on the one hand side. Even in these non-collinear structures, there's lots of things to learn and gain from that. But this is already so far that you can even go for tunneling magnetoresistance experiments now in these structures. In altermagnetism, things start now, but you have also this prospect of going for magnetoresistance effect. So it could be that there's a giant magnetoresistance effect that you can study, and you also can use it for spin splitter torque. But there's also nice things that you might be able to learn about the other excitations that you find in these altermagnetic structures. Okay. So now I'm switching over. And first of all, the most important thing before talking about the work that we have been doing, which is a little bit different from at least altermagnetism, is that the people that contributed to the work, I'm especially proud of all the PhD students that did a lot of the experimental work that I will be showing to you. And I'm deeply thankful to Akash that he always has an open ear for my weird measurements and comes up with some theory that plausibly explains what we are seeing here. And last but not least, Richard is there in the back. Sebastian is here. I'm really glad to work together with you guys in this thing. So what I want to talk about is, in the end, a scheme that allows us to investigate Magnon transport or Magnon spin transport in a system using just typical electronic transport structures. For this, I need two ingredients, and we will talk about this now. On the one hand side, I'm talking about this typical depiction of a pure charge and a pure spin current in the electronic picture, where you have spin up and spin down electrons that can, here on this depiction, you have the same number of spin up, spin down electrons moving in the same direction, meaning there's only charge transported, but no spin. But you can also do the opposite thing, saying, okay, spin up moves here upwards, spin down moves here downwards, and this way, net charge current is zero, but you have a finite charge current in the system. And as you all know, there is the spin Hall effect due to spin-orbit interaction in the system. If you take, for example, platinum, you apply a charge current to it, you will have a transversal spin current that is generated, and this will lead, in the end, to a spin accumulation at the top and bottom interfaces. Of course, one of the problems or challenges here is that the spin accumulation dies down rather quickly in these materials with large spin-orbit coupling. So spin decay length in the system is about a couple of nanometers, so you need to work with thin film structures to be able to access these phenomena. But this allows you to transfer a charge current into a spin current. And of course, there's also the reciprocal effect that allows you to now, if you would have a spin current that is injected in such a heavy metal system, it will transform it into a charge current. So with this, you have an access to inject spin current into a system and to detect spin current into a system. The next thing you need to do is now interface this non-magnetic metal, as I call it, with a magnetically ordered insulator. Why you want to take an insulator? Well, this allows you to avoid any issues about charge current transport, because this is an insulator, so there will be no mobile electrons inside the system down here. So you only need to worry about spin current physics in the system. And now the important thing is you have kind of this charge to spin current conversion with a certain spin orientation in the structure. And inside this magnetically ordered insulator, you have an order parameter, that could be the Néel vector, could be the magnetization, that you align in parallel or collinear fashion to the spin orientation. If you now have finite temperature, so you get some thermal magnum population in your system, you can directly access this thermal magnum bath and interact with that at this interface here. So if there's electron spin flip scattering, you can generate a magnon, or you can absorb a magnon with opposite chirality in the system. And with this, you change locally the thermal magnon gas in the system. So we get a higher occupation or a lower occupation in the system. Of course, if you think about charge current, one of the issues is still there will be also Joule heating due to the fact that you have a finite resistance. It will get warm, and this will also lead to some additional transport phenomena that you need to take into account. If you now generate a structure where you have two platinum electrodes sitting over here at this spot and over there, so typical dimensions are a couple of 100 nanometers in width and something like 50 to 100 micron in length, and then a separation that is of the order of micron, you can then work with these magnon transport experiments. So here on this left-hand side, you drive a charge current through this platinum strip. This will give you a spin current that's injected over here, leads to a magnon accumulation down there, and these magnons will then diffusively be transporting spin current over to the second electrode, where then a spin current is injected, transformed into a charge current, and as it's easier to measure, we use an open voltage signal that we detect over there. And there has been lots of work pioneered in the beginning by Ludo Cornelissen and Bart van Wees group. And then, as Gerrit already mentioned once, Sebastian was picking up quickly the pace, and then we kind of worked lots of things. And I would also like to mention that Matthias Cloy was with his group, and Romain Lebrun, the first ones that then showed that you can also do this instead of yttrium iron garnet, work with a antiferromagnetic system. Now, if you think about an antiferromagnetic system, I already was talking a little bit about these magnon modes that you see in this, and I would discern now very simply between so-called uniaxial or easy axis antiferromagnetic system. In this system, you will have two magnon modes that are left and right circularly polarized. And the nice thing is now you could also think about this left and right circular polarization, meaning they carry angular momentum of plus or minus h bar in the system. So you could think about spin up, spin down, or spin up magnons in this case. So this is very similar to the two electronic spin states in the system, so spin up and spin down electrons. So this also allows you then to envision either a so-called pure magnon current, where you have the same number of spin up magnons and spin down magnons moving in the same direction. So in this way, there will be no spin transported, only energy in the system. Or you can also go into this direction of having a pure spin current in the end, where these magnons move in opposite direction. Of course, this is already triggering the question, can you find now phenomena in this magnetic transport that you do with these magnons that are similar to what you would get from an electronic spin transport structure? On the other hand, if you think about an easy plane antiferromagnet, there you will have the eigenmodes as linear polarized modes. So there's one mode that is oscillating here in this plane, and another one that is oscillating out of this plane. And if you go to large K values, also these two modes will be energetically degenerate in the system, because the antiferromagnetic exchange is dominating at these cases. And what I would like to take you now through is really one of the phenomena where you could show that indeed there is phenomena that you can find in electronic spin transport that will also be developing in these magnonic systems. And one of the hallmark experiments is the Hanle effect. And I will try to introduce to you now the Magnon-Hanle effect in the system. So here, Akash is the one guy that is responsible for the theory work behind it. And this concept comes in the end with an idea to map out these different Magnon states that you can have in a system. So as you can see here, we have kind of this Bloch sphere. Okay. Now it's coming. Okay. So it is this Bloch sphere in the system, and here we have a mapping now of this Bloch sphere onto different magnonic excitations. So in this depiction that I showed to you here, we have these two linear polarized Magnon modes that are sitting here on these pole points. That will be the eigenstates of a easy plane antiferromagnet. And now if we go into the equatorial plane, we have now superposition states of these two modes. And this will be, of course, right circularly and left circularly. If you have kind of the right phase matching, you will get from these linear polarized modes circularly polarized modes, similarly as it's the case with light in a system. But you will also have two additional orthogonally linear polarized modes in the system. And now with this pseudospin that will live inside this mapping structure, you can determine this polarization and can describe the system, also the superposition stage, just by this pseudospin vector in the system. So you have a mapping that allows you to figure this out. And this is a pseudospin because it behaves also from the symmetry as a typical spin in the system. Now, the question that we wanted to address is really in this transport structure. We talked about, okay, you have spin up and spin down magnons. But the question would be, if you have now a system where these two are coupled to each other, what happens in such a structure? And if you do that, this is kind of a very easy way to say, in the end, you need to break this rotational symmetry about the nil vector, which just means you need to have an easy plane antiferromagnet in the system, and then you immediately get out that these two modes will couple to each other. Then, if you want to describe the transport, you can map this out now onto this pseudospin vector in the system. And with this, you are able to diffusively describe this transport. So we have diffusion constant. Then there's a characteristic spin lifetime in the system. In addition, now you need to account for this coupling term. And this comes in as a precessional term in the end. So you have an omega times s. So omega will be oriented along this y direction here. So this means the pseudospin here will precess in that plane, as it's shown over here. So you get, if you would start with a certain orientation of your pseudospin vector in this direction here, over time it will evolve. So meaning if you transport it, it will change from being a spin +1 to spin 0, spin -1, and so forth. This was one of the things. So now you need to think about, okay, I said already, we need an easy plane anisotropy to get to this coupling. And we need, in addition, we also need to take into account that the system that we are studying, that you also have a DMI-induced canting. And if you then look into what this coupling, so this precession frequency in the end, is made up of, you find out that this is kind of a effective anisotropy contribution. And there's, with a minus sign, you need to take into account that you have a net magnetization coming from the canting that you can also then tune via an external magnetic field here. Then you can solve the diffusion equation of the system, assuming a certain boundary condition where you have a spin current injection at one side, and then the system, it will propagate in the system. And this gives you this nice formula over here. Let's not try to look too long at that. We can also do it in the experimental way. So here, this is now the first work that we have been doing with a rather thin hematite layer. Hematite shows a hexagonal structure. It has a DMI interaction that leads to this canting of the magnetic moments. Here it's this so-called easy plane phase in the system. For our thin films, in these first experiments, we did not see any Morat transition, so this sample always remained in this easy plane phase with the linear polarized Magnon modes. And now we do this Magnon transport experiments. We have an injector here on the left-hand side, driving a charge current through it, and detecting the voltage over here. To rule out any contributions from thermal transport, we do a so-called current reversal method, where you take voltage values at plus and minus, charge current applied to this injector here, measured over there, and take the difference of the two, and you would expect now only effects to remain that are linear in current. So any thermal contribution should drop out in these measurements. And the nice thing about this now with the net magnetization is also we can manipulate the orientation of the nail vector now with an external magnetic field. And this is what we then investigated here. And this is now an example of the antiferromagnetic Magnon-Hanle effect that we see. So you see here, this is the detector signal that we record as a function of the external magnetic field. And there's a characteristic peak that you find here in the signal. And here the two different colors represent two different structures where you have a different separation between these two platinum electrodes. So, but the peak is always at the same position. But if you now follow the evolution of the magnetic field of the signal, you see that it goes to 0 and then goes to negative values, and then it seems to go up a little bit. And this you can explain now nicely in the pseudospin picture. Here at this maximum that we see in the spin transport signal, this comes from the fact that here at this magnetic field value, we switched off the precession of the pseudospin. So you inject a spin current here on this side, it goes in, and the magnons transport it to the other side, where you can then identify a spin signal. If you go to this point here, where you get 0 signal, this is exactly the point where you have some precessional motion going on, but it will only precess so far that you have a linear polarized magnon mode underneath your detector, 0 spin, you will not get a signal. And if you go further, you can even then invert it, so you can change the spin orientation that comes out of the system. And of course, if you change the distance, the 0 crossing and the negative value will change now because the propagation distance is different in the system. And this is reminiscent of the electronic Hanle effect that you can also investigate if you do spin transport here, with the kind of main difference in the end that here our magnetic field really tunes this precession frequency via the canting, while here it's a transversally applied magnetic field that leads to a precessional motion of the electron spins in the structure, where you can immediately start at 0 magnetic field to reduce the effect. We looked also in more detail into this spin transport with the magnons in this hematite. And one next step that we now figured out is that you can even look into some non-reciprocal properties. The effects, as you will see, are small, but it's very surprising that even in this simple antiferromagnet hematite, you can find a non-reciprocal effect in these structures. And again, Akash helped us a lot in figuring out how to describe the system. In the end, what you now need, so initially you assumed you have a kind of k-symmetric magnon dispersion in the system. You need to break this symmetry in the system a little bit, such that you have some difference. If you go in plus k or minus k direction, there will be a difference in the energy of the magnons. And this will lead to an effect that gives you an asymmetric contribution to your Magnon-Hanle effect in the end. You can also envision this in a way as it's depicted over here. So on the one hand side, we inject magnons on the left and detect them on the right, or you could change the experimental configuration, say, okay, I drive here on the right-hand side, measure on the left-hand side. And with this additional symmetry breaking that you have in the magnon dispersion, you will see that this leads in the end to effect that kind of the effective field that the pseudospin precesses through is different if you go from left to right as you go from right to left. So you have a difference of the pseudospin rotation angle seen over there, which you should detect in the experiment. And if you go below, so this compensation field, where you have no precession, if you're below this, it should be this way. And the expectation from theory is that it changes sign if you are above this value. We set out to investigate such effects. For this, you need to do now angle-resolved experiments because the signals are so tiny in the asymmetry. So you rotate the magnetic field here in this plane, and with that, you have a chance to investigate this transport now, taking these two different configurations, closed symbols, left to right, open symbols, right to left. And then you see here now at 5 and at 6 Tesla, you will see that there At 6 Tesla, the data points nearly agree, but at 5 Tesla, you see that the open symbols are a little bit higher here on the left side and a little bit lower here on the right-hand side. Now you can take the difference of these two curves, or the sum of the two divided by 2, and plot this here. So you have a symmetric part and an antisymmetric part, and you can now fit it with a sine cube function down here and a sine square function over there to extract the amplitudes more easily. And if you do that, you find this characteristic magnetic field dependence. For the symmetric one, it's just the Magnum-Hanle effect that I've been already showing to you. But here, for the red data points here, that's the asymmetric signal, and you see it changes sign around the compensation point, already confirming what we expected from the theory. One of the problems is still the microscopic origin is unclear, so what causes this asymmetry in the minus k direction. So this is something we need to still analyze in the system. With this, I have still a couple of minutes to go, and I want to switch over to something that has been already presented yesterday at the poster session by Matthias. So what we were talking about is, in the end, so here I showed to you, you take platinum, a magnetic ordered insulator, and do this Magnum spin transport. We wanted to see if you can also do that just with a ferromagnetic metal and using just a diamagnetic insulator. In this case here, it's a yttrium aluminum garnet substrate, and trying to see if you can measure some signals if you drive a charge current over there and measure voltage over here. And if you do these experiments, you figure out that the only critical configuration where it's possible to see some signal is if the two magnetizations now are oriented in this out-of-plane direction, depicted now with these different rotation planes that you can do these experiments in, where you rotate, again, the magnetic field with respect to the sample. And you see some signal here. Again, we use a current reversal technique, so any thermal signals should not contribute to the signal that we are seeing. And we see this directional dependence. So we want to briefly go through why this kind of out-of-plane orientation of the magnetization is important for this effect. And for this, we have kind of the figuring out that if you drive now a charge current through the system, what you will get is, again, a transversal spin current. So there's some intrinsic spin Hall effect inside this ferromagnetic metal that will lead to an electron spin accumulation here on the left and right-hand side. The spins will be oriented parallel to the magnetization. Other orientations will dephase so quickly in the exchange field that you need to not worry about it. And this gives you this characteristic spin accumulation described by the spin-dependent chemical potential that gives here a certain length scale, typically a couple of nanometers, where you will have an electron spin accumulation. The nice thing is now that this electron spin accumulation can, or this electron spin current can interact with the magnonic system at finite temperatures. Again, the same phenomena that we already talked about beforehand. If you inject the spin current, you will generate magnons or absorb magnons in the system. The same thing will happen also intrinsically, now not across an interface. And you will get a magnon accumulation in the system. The magnon decay length is way longer, so in this way you will have a longer area where you have magnons accumulating in the system. And now there's a process, so this can be, as we shortly will discuss, either dipolar coupling effects over this short gap here, or the other way would be having a phononic transport down here that will lead to the fact that this magnon accumulation will be transported over here to lead to a magnon accumulation on the left-hand side, on the right-hand side, and then will decay into the system. But since this is a kind of accumulation here on this will give rise to a spin current again, and this can be transformed to the electronic state via the inverse process that happened on the left-hand side, and this will give you a finite signal in the system, so you will get a detector signal. If you rotate now the magnetization into the plane, the trick that you play here is that the thickness of our ferromagnets is way shorter than the width of these strips, so any accumulation of the magnons will be coming to zero because this thickness here is way smaller than this magnon decay length that we have in the system. And this way you have this distinct two geometries where you get this accumulation and coupling, and here you suppress it by the geometry of the system, and this gives you this cosine squared dependence that you can see over here in the structures. Now you can probe different materials to figure out if this effect persists, and this is what we have also done. You can find it in this nickel-nickel configuration that I already have shown to you, but you can also use permalloy, for example, cobalt iron, and you can also use mixed configuration, and you always will get a finite signal. It is only not possible to do it if you replace either one or both of these electrodes with platinum. Then you only get this flat line signal, so this is also some confirmation that this is only working if you have ferromagnets or magnetic order in the system, but it's universal. Now, talking a little bit about the transport mechanism, I already introduced to you that we can either think about a dipolar coupling, so you have some fluctuating magnetic moment over here, which will generate a stray field, and then we can get the dipolar coupling or the phonon-mediated coupling. And to investigate this, we looked into the distance dependence, and you can either now motivate a kind of 1/d scaling or an exponential scaling. If you look into these fits that we've done here, the exponential is not too far off. I mean, the 1/d dependence that we modulated gives us a better fitting. We cannot rule out both of the contributions easily, so can be dipolar or phonon coupling that mediates the spin current transport. Needs to be more done. So I'll flash shortly the summary here and only want to do a short advertisement. There will be a seminar upcoming this year in October where we have a quite well-renowned list of speakers, where also a couple are sitting here in the audience. If you're interested, this is the QR code to get to the web page, where you can, in about 2 weeks, also register for this seminar in Bad Honnef, and it would be really a pleasure to welcome some of you there. And with this, I go back to the summary, and thank you for your attention.